so the size we measure depends on where we choose to draw the line. In practice, astronomers usually define a planet's radius as the level in the atmosphere where the optical depth reaches a certain value, meaning where the atmosphere becomes thick enough to block a significant amount of light. It's a practical choice that allows for consistent comparisons, even if it doesn't represent a physical surface you could stand on. There are also cases where planets are detected directly, not just through their effects on their stars. This is called direct imaging, and it's one of the most challenging techniques in astronomy. To directly image a planet, astronomers have to block out most of the star's light, often using a device called a coronagraph. This creates an artificial eclipse, allowing faint objects nearby to become visible. This method works best for young, massive planets that are far from their stars. These planets are still warm and glowing from their formation, making them easier to see in infrared light. When a planet is directly imaged, its size isn't measured by a simple dip in light. Instead, scientists estimate its brightness and temperature, and use models to infer its radius. This approach is less precise than transit measurements, but it provides valuable information, especially for planets that don't transit their stars. Another subtle tool in the measurement toolkit is gravitational microlensing. This technique relies on the way gravity bends light. When a star passes in front of a more distant star, its gravity can act like a lens, magnifying the background star's light. If the foreground star has a planet, that planet can create a small additional blip in the magnification pattern. Microlensing can reveal planets that are far from their stars and even planets that are free-floating, not bound to any star at all. However, it usually provides limited information about size. It's better at telling us about mass and distance than radius, so for the largest planets, the most detailed size measurements usually come from transits, often combined with radial velocity data. But even with these methods, there are uncertainties. Measuring the size of a star is not always straightforward. Stars can vary in brightness, their surfaces can have spots and flares, their distances might not be known with perfect precision. All of these factors can affect the estimate of the planet's size. That's why astronomers often refine their measurements over time. A planet might be discovered with an initial estimate of its radius, and then, as better data comes in, that estimate might be adjusted slightly upward or downward. In some cases, a planet that was once thought to be among the largest might slip down the list as its size is revised. In other cases, a world that didn't seem especially remarkable at first might turn out to be more extreme than anyone realised. There's also the matter of stellar companions. Some stars are actually part of binary systems, with two stars orbiting each other. If this isn't recognised, it can affect the measurements. The light from the second star can dilute the transit signal, making the planet appear smaller than it really is. So part of measuring a planet's size is making sure you understand the entire system it's in, not just the planet itself. Another layer of complexity comes from the shape of the planet. Most size measurements assume the planet is roughly spherical. But as we discussed earlier, rapidly rotating planets can be noticeably flattened at the poles and bulged at the equator. For distant exoplanets, this effect is usually too subtle to detect directly. But in principle, a very fast-spinning, very large planet might appear slightly larger in transit than it would if it were perfectly round. There are even ideas about detecting this kind of flattening by looking at very precise transit light curves, where the shape of the dip might carry information about the planet's outline. This is still an area of active research, but it shows how detailed these measurements can become. When it comes to the largest planets, another important factor is temperature. A hot, inflated atmosphere can make a planet appear larger in optical wavelengths than it does in infrared. This is because different layers of the atmosphere become opaque at different wavelengths. So a planet's measured radius can depend slightly on what kind of light you're using to observe it. This means that size is not always a single, fixed number. It can vary depending on how you look. Astronomers often take this into account by measuring transits at multiple wavelengths and building a more complete picture of the planet's atmospheric structure. This kind of work has been done with space telescopes like Hubble and, more recently, the James Webb Space Telescope. By observing the same planet in different parts of the spectrum, scientists can see how its apparent size changes and infer the presence of clouds, hazes, and different gases. And for some of the largest, puffiest planets, these observations have revealed atmospheres that extend incredibly far from the planet's centre, sometimes to the point where the outer layers are being stripped away by the star's radiation. So in a very real sense, measuring a planet's size is also a way of measuring how it's interacting with its environment. There's also a statistical side to all of this. When astronomers talk about the largest planets, they're often comparing a group of planets that have been measured using similar methods. This helps ensure that the comparisons are fair. A planet measured by direct imaging might not be directly comparable to one measured by transits, because the uncertainties and assumptions are different. So part of the quiet work of planetary science is building catalogues, standardizing measurements, and carefully noting how each value was obtained. This might sound dry, but it's what allows scientists to say with confidence that one planet is larger than another, rather than just guessing based on incomplete information. There's also a sense of humility built into this process. Astronomers are always aware that their measurements are limited by their instruments and their models. They report uncertainties along with their values. A planet's radius might be listed as, say, 1.8 times that of Jupiter, plus or minus a small fraction. Those plus or minus numbers matter. They remind us that what we know is always an approximation, and yet, even with those uncertainties, a pattern emerges. Some planets are clearly much larger than others. Some clearly sit at the upper end of what we've observed so far. So when someone asks, "How do you know this is one of the largest planets ever discovered?" the answer is not a single measurement, but a web of observations. Light curves, spectra, stellar models, follow-up studies, comparisons across many systems. It's a collective effort, built over time, refined as new data comes in. There's something quietly satisfying about that. Worlds of immense scale are revealed through methods that depend on patience and attention to detail. A universe that builds planets the size of small stars is studied through changes in light that can be smaller than the flicker of a candle. As you let this idea settle, you might picture an astronomer watching a graph on a screen, a smooth line of starlight brightness dipping ever so slightly and then rising again. That small dip represents a world passing in front of its star, a world that might be larger than Jupiter, a world that might have an atmosphere stretching thousands of kilometers into space. From that tiny signal, an entire planet enters our understanding. Once you can measure a planet's size and mass, you can start to ask a deeper question. Not just how big is it, but what is it like inside? What is it made of? Why does it have the size and shape that it does? Somewhere in the quiet space between a star's steady glow and the careful attention of astronomers on Earth, a particular kind of question begins to take shape. It's not a loud or urgent question. It doesn't demand an immediate answer. Instead, it lingers, gently persistent, asking what happens when curiosity, technology, and the vastness of the universe meet at a single point of comparison. Out of that meeting comes the idea of a record, the largest planet ever found so far. That phrase, so far, does a lot of quiet work. It carries with it an understanding that what we know today may change tomorrow, that every list and every title is provisional, waiting for the next faint signal from a distant star to rearrange the order of things. Still, within the limits of what we've measured and confirmed, there are a few worlds that stand out as especially wide, especially inflated, especially difficult to ignore. To talk about the largest planet ever found so far, we have to return to the way astronomers usually define largest in this context. It almost always refers to size by radius or diameter, not by mass. The reason is practical. Size is what the transit method measures most directly. When a planet passes in front of its star, the amount of light it blocks tells us how wide it is, at least in terms of where its atmosphere becomes thick enough to stop starlight. Using that definition, the title of largest tends to go to planets that are not just massive, but also highly inflated. These are often gas giants orbiting close to their stars, their atmospheres expanded by intense heat and internal energy. One of the names that frequently appears near the top of these lists is a planet called WASP-17b. WASP-17b was discovered in 2009 as part of the Wide-Angle Search for Planets project, a survey designed to look for transiting planets around bright stars. When astronomers first analysed its data, they noticed something unusual. The dip in the star's light suggested a planet that was extraordinarily wide. Follow-up measurements confirmed it. WASP-17b has a radius nearly twice that of Jupiter. In some estimates, it reaches about 1.9 to 2 times Jupiter's radius, depending on the exact models and measurements used. To put that into a more tangible frame, Imagine Jupiter. Now imagine a version of it that stretches nearly twice as far from its centre in every direction. The volume of such a world would be more than 6 times greater than Jupiter's, even if the mass is much lower. It's a planet that takes up an enormous amount of space without containing a proportionate amount of material. That low density is one of its defining features. WASP-17b is often described as one of the puffiest planets known. Its mass is only about half that of Jupiter, yet its size is nearly double. That combination makes it incredibly light for its volume. If you could somehow stand on a solid surface inside this planet, which is a purely hypothetical exercise, the gravity would feel much weaker than Jupiter's, even though the world itself is far larger. The mass is spread out over a much bigger region, so the pull at the outer layers is relatively gentle by giant planet standards. WASP-17b orbits its star at a very close distance, completing a full orbit in just a few days. This proximity exposes it to intense radiation, which heats its atmosphere and keeps it expanded. The planet is also notable for its unusual orbit. It appears to orbit in a direction opposite to the rotation of its star, a retrograde orbit that suggests a turbulent past, possibly involving gravitational interactions with other planets or stars. This combination of extreme size, low density, and odd orbital behaviour makes WASP-17b feel like more than just a record holder. It feels like a case study in how flexible and creative planetary systems can be. Another planet that often enters the conversation is HAT P67b. This world is also remarkably large and even less dense than WASP-17b. It has a radius close to twice that of Jupiter and an incredibly low mass for its size. HAT P67b orbits a star that is larger and hotter than the Sun, and like many of these oversized giants, it sits very close to its star. The heat it receives helps keep its atmosphere in an expanded state. What makes HAT P67b especially interesting is how close it comes to the boundary between planet and something else. Its host star is in a later stage of its life, beginning to expand into a subgiant. As the star grows, it may eventually engulf the planet, ending its existence in a slow, inevitable way. So when we talk about the largest planet ever found so far, we're often talking about worlds that may not be long for the universe in their current form. They're caught in a phase where they are at their biggest, before time and stellar evolution reshape them. There are other candidates as well, planets like TREES 4b, Kepler 12b, and Kelt 11b, each with radii significantly larger than Jupiter's. These worlds all share similar traits. They are close to their stars, they are hot, they are low in density, and they challenge the simple idea that a planet's size should scale neatly with its mass. But here's where the phrase, "ever found so far," becomes especially important. The list of largest planets is not fixed. It changes as new discoveries are made and as existing measurements are refined. For example, a planet might initially be reported as having a radius of 2.1 times that of Jupiter. Later, with better data on the star's size or distance, that estimate might be revised down to 1.9. Another planet might be discovered with an even larger estimated radius, but with larger uncertainties. So astronomers tend to be cautious about declaring a single permanent champion. Instead, they often talk about a small group of planets that occupy the extreme upper end of the size range. There's also a deeper question hiding beneath the surface. Are these planets truly the largest that exist, or just the largest that are easiest for us to find? The transit method favours large planets close to bright stars. These are the ones that create the most noticeable dips in starlight. So our sample of known oversized planets is shaped by our detection techniques. It's possible that there are planets even larger than WASP-17b or HAT P67b, orbiting farther from their stars or around dimmer stars, where they are harder to detect. These worlds might not transit from our point of view. They might not cause a large enough wobble in their stars to be easily measured. So the title of largest is not just a statement about the universe, it's also a statement about our tools. That doesn't make these discoveries any less impressive. It just places them within a broader context of ongoing exploration. Another interesting angle is the relationship between size and survival. These extremely inflated planets are often in precarious positions. Their atmospheres are extended and loosely bound, making them vulnerable to being stripped away by their stars. Some of these planets show signs of atmospheric escape. Observations in ultraviolet light have revealed streams of gas trailing behind certain hot Jupiters, like invisible tails. Over long periods of time, this process can significantly reduce the planet's mass and size, so the largest planet ever found so far might represent a temporary state, a moment in a planet's life when it is at its most expanded, before it gradually shrinks or transforms into a smaller, denser world. In that sense, the record holder is not just a static object, it's a snapshot in a long story of change. There's also the question of what lies just beyond the category of planet. As we discussed earlier, objects more massive than about 13 times Jupiter's mass confuse deuterium and are often classified as brown dwarfs. Some of the most massive objects in this range have sizes similar to Jupiter, not much larger. They don't tend to be record holders for diameter because their strong gravity compresses them. So the largest planets by size tend to be relatively light for their volume, sitting comfortably below the brown dwarf threshold. This creates an interesting contrast. The biggest looking planets are not the heaviest. They are in a way the most delicate giants. There's something quietly poetic about that, even without leaning into metaphor. The worlds that take up the most space are not the ones with the most substance. They are the ones that have found a way to stretch out, to hold on to heat and gas, to occupy a wide region of space with relatively little mass. From a scientific perspective, these planets are valuable because they test the limits of our models. They force scientists to consider how energy moves through a planet's interior, how atmospheres respond to extreme radiation, and how gravity and temperature balance each other. For example, one of the puzzles is why some hot Jupiters are much more inflated than others at similar distances from their stars. There may be differences in their internal structure, their magnetic fields, or their atmospheric circulation that affect how they transport and retain heat. Another possibility is that the presence of heavy elements in the planet's core or atmosphere can influence how efficiently it radiates energy into space. A planet with more heavy elements might cool and contract faster, becoming more compact over time, so the largest planets offer a way to probe these internal processes, even though we can't see inside them directly. There's also a sense in which these worlds serve as bridges between categories. They sit between the familiar gas giants of our solar system and the small stars and brown dwarfs that begin to glow on their own. They show us what happens when you push a planetary system to its extremes without quite crossing over into something fundamentally different. From a human perspective, there's something appealing about having a largest anything. It gives us a point of reference, a way to anchor our imagination. But as you spend time with the details, that anchor starts to feel less like a fixed post and more like a floating marker. It tells you where the edge of your knowledge is, not where the edge of the universe lies. Because beyond WASP-17b, beyond HAT P67b, beyond every name we've written into our catalogues, there are countless stars we haven't studied closely yet. There are regions of the galaxy we haven't surveyed in detail. There are planetary systems that haven't had their light curves plotted or their spectra analysed. Somewhere among those unexamined points of light, there may be worlds that are larger, more inflated, or more extreme than anything we've seen so far. Or it may be that nature really does impose a soft limit, and the planets we've already found are brushing up against it. Either way, the question remains open. It's also worth noticing how these discoveries shape our sense of scale back here on Earth. Thinking about a planet twice the size of Jupiter can make even the largest things in our everyday lives feel small by comparison. Cities, mountains, oceans all become tiny features on a world that itself would be a small dot next to one of these giants. But there's a balance to that thought. These enormous planets, for all their size, are still just parts of larger systems. They orbit stars. Those stars orbit the centres of galaxies, and those galaxies are part of a wider cosmic web. So, largest is always relative. It depends on what you're comparing and how far out you zoom. What processes cause a planet's atmosphere to expand into such a wide, diffuse envelope? What keeps it there, and what eventually allows it to shrink back down? Across the long stretch of space between a star's steady glow and the drifting path of a planet, there is a constant exchange of energy that rarely draws attention to itself. It doesn't announce its presence with flashes or sounds. It simply flows, quietly, from one body to another, shaping atmospheres, stirring winds, and, in some cases, causing entire worlds to expand beyond what seems reasonable. This slow, persistent flow is at the heart of why some planets swell until they look more like soft, overfilled shapes than the compact spheres we might expect. To understand this gentle swelling, it helps to start with a simple idea from everyday experience. When you heat something, it usually expands. Air in a balloon spreads out when it gets warm. Metal rails on a hot day grow slightly longer. Even a cup of water will rise just a bit in volume as its temperature increases. The same basic principle applies to planetary atmospheres, but on a scale that stretches across thousands of kilometers. For a gas giant orbiting close to its star, heat is not an occasional visitor. It's a constant companion. The star's light and radiation pour into the upper layers of the planet's atmosphere, warming the gas and giving its particles more energy. As those particles move faster, they push outward, causing the atmosphere to puff up and occupy a larger region of space. This alone can explain some amount of swelling, but it doesn't tell the whole story. If heat from the star were the only factor, then every close-in gas giant would look roughly the same size given similar mass and distance. In reality, they don't. Some planets remain relatively compact, while others balloon outward to astonishing proportions, so astronomers began looking deeper, not just at what's happening on the outside, but at what's going on inside these worlds. One important factor is how a planet handles the energy it receives. When a planet absorbs heat, it doesn't all stay in the atmosphere. Some of it is carried deeper into the interior. The way this energy moves depends on the structure of the planet, its composition, and the motion of its atmosphere. In some planets, strong winds can transport heat from the day side, the side facing the star, to the night side. This circulation can drive energy deeper into the atmosphere, warming layers that would otherwise remain cooler. That deeper heating can cause the planet to expand from the inside out, not just at the surface. Think of it like warming a loaf of bread in an oven. If only the crust gets hot, the loaf doesn't change much overall. But if the heat penetrates deeper, the whole loaf can expand slightly as the air inside warms and spreads. Another source of internal energy comes from the planet's own history. When a giant planet forms, it starts out hot. The process of gathering gas and collapsing under gravity releases energy, and that energy is stored as heat inside the planet. Over time, the planet slowly radiates that heat into space and cools down, which can cause it to contract. But if something interferes with that cooling, the planet can stay larger for longer. One way this can happen is through tidal heating. If a planet's orbit is not perfectly circular, its distance from its star changes slightly as it moves around. The star's gravity pulls on the planet more strongly when it's closer and more weakly when it's farther away. This changing pull can flex the planet's interior, generating heat through friction, much like bending a piece of wire back and forth makes it warm. This process is well known in our own solar system. Jupiter's moon, Io, is heated by tidal forces from Jupiter and the other Galilean moons, and that heat drives its intense volcanic activity. For a close-in giant planet, tidal heating can occur on a much larger scale. If the planet's orbit is slightly stretched, or if it's being influenced by another planet in the system, the resulting internal heating can add to the energy coming from the star. This extra heat can keep the planet's interior warm and its atmosphere expanded. Another layer of complexity comes from the planet's magnetic field. A strong magnetic field can interact with the stellar wind, the stream of charged particles flowing out from the star. When these particles collide with the planet's magnetosphere, they can deposit energy into the upper atmosphere. This process is similar in a broad sense to what creates auroras on Earth, but on a giant planet close to a star it can happen on a much larger scale, potentially contributing to the heating and expansion of the atmosphere. Composition also plays a role. Not all gases behave the same way when heated. Some are better at absorbing and trapping energy. If a planet's atmosphere contains certain molecules, they can act like a blanket, holding onto heat and preventing it from escaping easily. Water vapor, carbon compounds, and other heavier molecules can increase the atmosphere's ability to retain energy. This can slow the planet's cooling and help maintain an inflated state. There's also the matter of how the planet's interior is layered. Some models suggest that certain giant planets may have regions where heavier elements are mixed in with lighter gases in ways that affect how heat moves through the planet. If heat has a harder time escaping from the interior, the planet can remain swollen for longer periods. This idea of heat transport is central to understanding why two planets that look similar on the outside can have very different sizes. One might efficiently radiate its internal heat into space and gradually contract. The other might trap that heat, staying larger and puffier. Age, once again, plays a role here. Younger planets are generally hotter and larger. Over time, as they cool, they shrink. So when astronomers observe a particularly inflated planet, one of the questions they ask is whether it's relatively young. But this isn't always enough to explain what they see. Some planets appear to be billions of years old and still remarkably large. That suggests there are ongoing processes keeping them inflated, not just leftover heat from their formation. Another factor to consider is atmospheric escape. This might seem like it would make a planet smaller, not larger, but the process can be more subtle. When the upper layers of a planet's atmosphere are heated by intense radiation, some of the gas can gain enough energy to escape into space. This creates a flow of material away from the planet, sometimes forming a long, invisible tail. This escape process can alter the structure of the atmosphere. It can remove lighter gases from the upper layers, changing the way the remaining atmosphere absorbs and redistributes heat. In some cases, this can lead to a reorganization of the atmospheric layers that temporarily enhances the planet's apparent size in certain wavelengths of light. So even the loss of material can, in a complex way, be part of what makes a planet look swollen when we measure it. It's also worth thinking about the role of clouds and hazes. Many giant planets have thick cloud layers made of compounds that would be exotic on Earth, such as silicates or metal oxides. These clouds can sit high in the atmosphere, blocking starlight at higher altitudes. When astronomers measure the size of a planet using the transit method, they're measuring where the atmosphere becomes opaque to light. If a planet has high-altitude clouds or hazes, that opaque layer can be farther out, making the planet appear larger than it would if the atmosphere were clear. So in some cases, part of a planet's swollen appearance might come from the way light interacts with its atmosphere, not just from the physical expansion of the gas itself. Another piece of the puzzle is the relationship between mass and radius. As we discussed earlier, adding mass to a gas giant doesn't always make it bigger. At some point, the extra gravity compresses the planet, so the planets that tend to look the largest are often those with relatively low mass for their size. They have enough gravity to hold onto a thick atmosphere, but not so much that they squeeze it into a compact shape. This creates a kind of sweet spot for inflation. Planets in this range can puff up dramatically when heated, while more massive planets remain relatively compact even under similar conditions. There's also an interesting feedback loop at work. As a planet's atmosphere expands, the gravity at the outer edge becomes weaker because you're farther from the centre of mass. This can make it easier for the atmosphere to stay extended and even for some of it to escape. That escape can then change the composition and structure of the atmosphere, which can affect how heat is absorbed and retained. So the planet's size, gravity and atmosphere are all tied together in a dynamic balance, each influencing the others over time. Another thing to consider is the star itself. Not all stars are the same. Some are more active, producing strong stellar winds and frequent flares. These can deliver bursts of energy to a planet's atmosphere, heating it and potentially driving changes in its size. Stars also change over time. As a star ages, it can become brighter and larger. A planet that formed at a comfortable distance might find itself exposed to much more intense radiation later in its life, which could trigger or enhance atmospheric inflation. So a planet's swelling is not just about the planet, it's about the ongoing relationship between the planet and its star. There's also a subtle observational angle to all of this. The size we measure for a planet depends on the wavelength of light we're using. Different gases and particles in the atmosphere block different kinds of light at different altitudes. In visible light, a planet might appear a certain size. In infrared, where we're looking at heat rather than reflected light, it might appear slightly smaller or larger, depending on the structure of the atmosphere. By comparing measurements across different wavelengths, astronomers can build a more detailed picture of the planet's atmospheric layers and how far they extend. For some of the most inflated planets, these multi-wavelength observations have revealed atmospheres that stretch so far from the planet's centre that they're only loosely bound by gravity. In these cases, the line between the planet and space becomes especially blurred. This brings us back to the idea of limits. How big can a planet get before it stops being a planet in any meaningful sense? If its atmosphere is constantly flowing away into space, if its outer layers are shaped more by the star's radiation than by the planet's own gravity, at what point does it become something more like a cloud than a world? These are not just philosophical questions, they tie directly into how scientists classify and understand what they observe. From a modelling perspective, explaining planetary inflation has been one of the more challenging problems in exoplanet science. Simple models that include only heating from the star often fall short of reproducing the most extreme cases. That's why researchers continue to explore combinations of effects, tidal heating, magnetic interactions, atmospheric chemistry, and internal structure to see how they might work together. There's also ongoing work to understand how stable these inflated states are. Are they long-lasting, or are they brief phases in a planet's life? Do all close-in gas giants go through a swollen stage, or only some of them? The answers to these questions will shape how we think about the largest planets ever discovered. If inflation is a temporary phase, then the largest planets might simply be those we happen to catch at the right moment. If, on the other hand, some planets can remain inflated for billions of years, then these oversized worlds represent a stable class of giant planets, not just a fleeting curiosity. There's a quiet beauty in how all of this comes together. A planet's size is not just a number, it's the outcome of a long, ongoing conversation between gravity and heat, between formation and environment, between the planet and its star. Every swollen giant carries within it a record of that conversation. In its extended atmosphere, in its low density, in its response to radiation and tides, you can read hints of how it formed, how it moved, and how it has been shaped over time. You might picture one of these inflated planets drifting close to its star, its atmosphere glowing faintly, stretched outward by heat and motion. The star's light washes over it constantly, and the planet responds by expanding, shedding, and reshaping itself in a slow, steady rhythm. At a certain point in the quiet climb from small to large, from light to heavy, from cool to hot, the universe begins to blur one of its own categories. The difference between a planet and a star, which feels so clear when you're looking at Earth and the Sun, becomes much less obvious when you start exploring the massive worlds that sit near the upper end of what we call a planet. Somewhere in that wide, dimly lit region of possibility lives a class of objects that don't fit comfortably into either box. They are not quite planets. They are not quite stars. They are the in-between, and they mark the thin line that challenges how we define what a world really is. To understand this boundary, it helps to start with what makes a star a star. A true star shines because of nuclear fusion. Deep in its core, hydrogen atoms are pressed together under enormous pressure and temperature, merging to form helium and releasing energy in the process. That energy flows outward, eventually reaching the surface and radiating into space as light and heat. This process requires an incredible amount of mass. Gravity must be strong enough to squeeze the star's core to temperatures of millions of degrees. Without that mass, the pressure never gets high enough for fusion to begin, and the object remains dark, at least in terms of generating its own light. Planets, even very large ones, don't reach those conditions. They may be hot inside, they may glow faintly from leftover heat of formation, but they don't have the sustained nuclear reactions that define a star. Between these two categories sits a group of objects known as brown dwarfs. They are sometimes called failed stars, although that name can be a little misleading. It suggests that they tried to become stars and didn't quite make it, when in reality they are simply objects that formed in a way similar to stars but didn't gather enough mass to fully ignite. Brown dwarfs form from collapsing clouds of gas, much like stars do. They don't necessarily form in disks around other stars the way planets do. Instead, they can form on their own, directly from a region of gas that becomes dense enough to collapse under its own gravity. Because of this, brown dwarfs often start their lives hot. They glow in infrared light, radiating the energy from their formation. Over time, they cool and fade, becoming dimmer and harder to detect. There is a particular threshold that often gets used to draw a line between planets and brown dwarfs. That threshold is related to a type of nuclear fusion that involves deuterium. Deuterium is a heavier form of hydrogen. It has one proton and one neutron in its nucleus, rather than just a single proton like ordinary hydrogen. Fusing deuterium requires less extreme conditions than fusing regular hydrogen. It can happen at lower temperatures and pressures. Objects with about 13 times the mass of Jupiter are thought to be massive enough to briefly fuse deuterium in their cores. They don't sustain this process for billions of years the way stars do. but they can do it for a short time early in their lives. So by one common definition, anything above about 13 Jupiter masses is considered a brown dwarf, and anything below is considered a planet. This seems like a neat, tidy rule. But as with many things in astronomy, reality doesn't always stay neatly inside the lines. For one thing, that mass limit isn't exact. The exact threshold for deuterium fusion depends on the object's composition. An object with a slightly different mix of elements might start fusing deuterium at a slightly lower or higher mass. For another, the ability to fuse deuterium doesn't necessarily reflect how the object formed. A very massive planet that formed in a disk around a star could, in theory, cross that 13 Jupiter mass line and briefly fuse deuterium, even though its origin was planetary, not stellar. So you could end up with an object that looks like a planet in terms of its formation history, but behaves like a brown dwarf in terms of its internal physics. This is where the thin line becomes less of a line and more of a zone. There are objects known as super-Jupiters that sit right near this boundary. They have masses several times that of Jupiter. Some are 10, 12, or even 15 times as massive. Depending on how you define things, some of these might be called planets, others might be called brown dwarfs. What makes this especially interesting is that, in terms of size, these objects often look very similar. A super-Jupiter with 10 times Jupiter's mass might have almost the same radius as Jupiter. A brown dwarf with 20 times Jupiter's mass might also have a radius not much different. This happens because as mass increases in this range, gravity compresses the object more and more. The extra material doesn't make it wider, it makes it denser. So you can't easily tell whether something's a planet or a brown dwarf just by looking at how big it is. You need to know how heavy it is, and ideally, how it formed. From an observational standpoint, that's a challenge. It's much easier to measure size than it is to determine formation history. So astronomers often find themselves working with incomplete information. They can measure a planet's radius from transits. They can estimate its mass from stellar wobble. But figuring out whether it formed in a disk or collapsed from a cloud is much harder. In some cases, the environment provides clues. If a massive object is found very close to a star, in a tight planet-like orbit, it's more likely to have formed in a disk. If it's found far away, on a wide star-like orbit, or drifting alone through space, it might be more likely to be a brown dwarf. But these are general trends, not hard rules. There are even objects known as free-floating planets, worlds that don't orbit any star at all. Some of these may have formed in disks and been ejected. Others may have formed more like brown dwarfs. From a distance, they can look very similar. So the thin line between planet and failed star is not just about mass, it's about history, environment, and behaviour. Another piece of this boundary comes from internal structure. Planets that form in disks tend to build up a solid core first, then gather gas around it. Brown dwarfs, forming from collapsing clouds, may be more uniform throughout without a distinct core. If we could look inside these objects, we might be able to tell them apart more easily. But since we can't, we rely on indirect measurements and models. There's also the matter of luminosity. Young brown dwarfs can be quite bright in infrared light, because they're still hot from their formation, and from any deuterium fusion they may have experienced. Massive planets can also be bright when they're young, but they tend to cool and fade more quickly. So in very young systems, it can be especially hard to tell whether a glowing object is a planet or a brown dwarf. This ambiguity becomes particularly relevant when we talk about the largest planets ever found. Some of the most massive objects that get included in these discussions are right at the edge of the brown dwarf category. Depending on how strict you are with definitions, the largest planet might actually be something that another astronomer would call a failed star. This isn't just a semantic issue, it affects how we interpret the object's place in its system. If it's a planet, it likely formed as part of a planetary system, and may have influenced the formation and evolution of other planets around the same star. If it's a brown dwarf, it might be more like a companion star, shaping the system in a different way. So classification matters for understanding the broader story of how systems form and evolve. There's also a cultural side to this boundary. The word planet carries a certain weight in the human imagination. It's just a world, a place, something you might, at least in theory, imagine visiting or standing on. The word star suggests something much more remote, much more powerful, something that defines a system rather than being part of one. Brown dwarfs sit in between these ideas. They are worlds in the sense that they are objects you could orbit. Some of them even have their own planets, but they are also star-like in their formation, and, at least early on, in their behaviour. So when astronomers debate whether a particular object is a planet or a brown dwarf, they're not just sorting things into bins, they're deciding how that object fits into the larger story of the universe. There's a deeper question here about how much our categories reflect reality, and how much they reflect our need for tidy labels. The universe doesn't seem to care about our definitions. It produces objects across a continuous range of masses, sizes, and properties. We draw lines through that range to make sense of it, but those lines are human inventions. That doesn't mean they're useless. On the contrary, they help us organise our knowledge and communicate with one another, but they are always approximations. The thin line between planet and failed star is a reminder of that. From a scientific perspective, this boundary is also a place of opportunity. Objects near this line can tell us a lot about how stars and planets form. By studying their properties, astronomers can test models of disk formation, cloud collapse, and the role of environment in shaping different kinds of objects. For example, if we find a massive object near the brown dwarf boundary in a tight, planet-like orbit, that might suggest that planetary disks can sometimes produce very massive worlds. If we find similar mass objects mostly on wide, star-like orbits, that might suggest that they form more like stars. So these borderline cases become important data points. There's also an interesting connection to the search for the largest planets. The fact that size and mass don't scale neatly in this range means that the largest looking planets are not necessarily the ones closest to this boundary. In fact, as we've seen, the most massive objects tend to be more compact. The puffiest, widest planets are often much lighter. So the largest planets by size are not the ones that are about to become stars. They are in a way at the opposite extreme. They are the most extended, the most diffuse. So the thin line between planet and failed star runs almost perpendicular to the line between small and large in terms of radius. One is about mass and internal physics, the other is about heat, atmosphere and expansion. That creates a kind of cross-shaped landscape of possibilities, where you can have small but heavy objects, large but light ones, and everything in between. As astronomers continue to explore this landscape, they keep refining their tools. New telescopes, more sensitive instruments, and more detailed models allow them to probe these objects in greater depth. The James Webb Space Telescope, for example, is capable of studying the atmospheres of giant exoplanets and brown dwarfs in unprecedented detail. By looking at their chemical makeup, temperature profiles, and cloud structures, scientists can gain insights into how these objects formed and how they differ from one another. Over time, this may help sharpen the boundary, or at least make its nature clearer. But it's also possible that the boundary will remain fuzzy, because the universe itself is fuzzy in this region. There may always be objects that sit comfortably in the grey area, refusing to be easily classified. There's something quietly fitting about that. The most interesting places in science are often the ones where categories break down, where simple rules stop working, and where deeper understanding is required. The thin line between planet and failed star is one of those places. As you let this idea settle, you might picture a massive object drifting through space, glowing faintly with internal heat, orbiting a star or perhaps wandering alone. Is it a planet? Is it a star that never quite ignited? The answer might depend on which part of its story you focus on. And that sense of open-endedness brings us back to the broader theme of this journey. The search for the largest planet is not just about finding something bigger than everything else. It's about exploring the edges of what we know, the places where definitions soften and understanding deepens. Beyond the list of names and numbers that fill astronomy catalogues, there's a quieter, more open-ended kind of question that tends to linger in the background. It doesn't ask for a record or a ranking, it asks about possibility. If we've already found planets that stretch nearly twice the size of Jupiter, if we've seen worlds so puffed up they barely seem held together, then what lies just beyond the edge of what we know? Could there be planets even larger, even more extreme, waiting in parts of the universe we haven't looked closely enough yet? To sit with that question, it helps to step back from individual discoveries and think about the universe as a whole. The galaxy we live in, the Milky Way, contains hundreds of billions of stars. And beyond it, there are billions of other galaxies, each with their own stars, their own disks of gas and dust, their own opportunities for planets to form. The number of planetary systems in the observable universe is so large that even conservative estimates start to feel abstract. So when we ask whether larger planets could exist, we're not just asking about a few systems we've studied so far. We're asking about what might be possible across an enormous range of environments, star types, chemical compositions, and histories. One way to approach this is to look at the ingredients. Planet formation depends on three main things: material, time, and conditions. You need a disk of gas and dust around a young star. You need enough time for that material to clump together. And you need conditions that allow a growing world to hold on to what it gathers. If any one of these factors changes, the outcome can change dramatically. Consider material first. Some stars form in regions that are richer in heavy elements than others. Astronomers often refer to this as metallicity, which in this context means the abundance of elements heavier than hydrogen and helium. A disk with more heavy elements can build solid cores more efficiently, which can help form giant planets more quickly. In such environments, it's easier for a core to reach the critical size needed to start pulling in large amounts of gas before the disk dissipates. That opens the door to the formation of very massive, very gas-rich planets. Now imagine a region of space where star formation is especially active, where clouds of gas and dust are dense and rich. In those regions, disks might be larger and more massive than average. A planet forming in such a disk could, in principle, have access to more raw material than the ones we typically observe around nearby stars. More material means more potential for growth. But even with abundant material, there are still physical limits. Gravity, pressure, and temperature shape what a planet can become. As a planet grows more massive, its gravity compresses it. As it becomes hotter, its atmosphere expands. These two effects push against each other. The planets that look the largest by radius tend to be in a sweet spot. They are massive enough to hold onto thick atmospheres, but not so massive that their gravity squeezes them into compact forms. They are hot enough to inflate, but not so hot that they lose their atmospheres entirely. So if we're looking for planets larger than anything we've seen so far, we might expect them to exist in environments that favour this balance. Perhaps they orbit stars that provide steady, intense heat, without extreme flares. Perhaps they formed in disks that were just massive enough to build a solid core and then supply large amounts of gas, but not so massive that the planet crossed into the brown dwarf range. There's also the factor of age. Younger planets are often larger. They haven't had time to cool and contract, so if we look at very young star-forming regions, we might find giant planets that are temporarily much larger than their older counterparts. Some of the largest objects found through direct imaging, for example, are young, massive planets orbiting far from their stars. These planets are still glowing with the heat of formation. They appear large and bright in infrared light. As they age, they will cool, dim, and likely shrink. So in a sense, the universe might be full of planets that are, at certain moments in their lives, larger than anything we've catalogued so far, even if they don't stay that way. Another angle to consider is the diversity of stars themselves. Most of the planets we've discovered orbit stars similar to the Sun, or smaller, cooler stars known as red dwarfs. But the universe also contains much larger and more massive stars. Massive stars have stronger gravity, brighter light, and often shorter lifespans. The disks around them can be more massive as well, at least early on. That raises an interesting possibility. Could a very massive star host a planetary disk capable of forming truly enormous planets? There are challenges here. Massive stars emit intense radiation that can blow away the gas in their disks more quickly. That can make it harder for planets to form at all, especially giant ones that need time to gather gas. But if a planet were able to form quickly in such a disk, it might have access to a large reservoir of material. So these environments might be rare, but they could, in principle, produce unusual outcomes. There's also the question of where we look. Most planet hunting missions focus on stars in our relatively local region of the galaxy. These stars tend to have chemical compositions similar to the Sun's, but the Milky Way is not chemically uniform. Different regions have different histories of star formation and element production. The inner parts of the galaxy, closer to the galactic centre, tend to be richer in heavy elements. This is because many generations of stars have lived and died there, seeding the region with heavier materials. In such regions, planetary disks might be especially rich in the solid material needed to build large cores quickly. That could, in theory, increase the chances of forming massive gas giants. The challenge is that these regions are harder to observe. There's a lot of dust and gas between us and the galactic centre, which blocks visible light. Observations in infrared and radio wavelengths can penetrate this dust, but detecting transiting planets or measuring stellar wobbles in such crowded fields is difficult, so it's possible that some of the most extreme planets are hiding in places we haven't been able to study in detail yet. Another possibility comes from thinking about planetary systems that don't look like ours at all. In our solar system, the giant planets are well separated. They orbit at different distances, each with its own space, but in some exoplanet systems, planets are packed much more closely together. There are systems with multiple giant planets in tight orbits, interacting strongly with one another. In such systems, gravitational interactions can lead to dramatic events. Planets can be scattered into new orbits. Some can be ejected from the system entirely. Others can be pushed inward toward the star. A planet that is pushed inward might become a hot, inflated giant, swelling as it absorbs heat. If it started out massive and gas-rich, this process could create a world that appears exceptionally large, so the dynamics of a system, not just its initial conditions, can play a role in creating extreme planets. There's also the concept of free-floating planets, worlds that are not bound to any star. Some of these may have formed in disks and been ejected. Others may have formed more like brown dwarfs directly from collapsing clouds. If a massive free-floating planet exists, especially a young one, it could be quite large and warm. It wouldn't be heated by a star, but it would still be glowing with its own internal heat. These objects are difficult to detect because they don't cause transits or stellar wobbles. They're usually found through microlensing or direct imaging in infrared, so our knowledge of them is still limited. It's possible that some of the largest planetary mass objects in the universe are wandering alone, not orbiting any star, and therefore not easily found by the methods we use most often. Another factor to consider is time itself. The universe has been around for about 13.8 billion years. Over that time, conditions for star and planet formation have changed. In the early universe, there were fewer heavy elements. The first generations of stars formed in an environment dominated by hydrogen and helium. That might have made it harder to form planets with solid cores, and therefore harder to form giant planets. As time went on, and more stars lived and died, the universe became richer in heavier elements. That made it easier for planets to form, especially large ones. So there may be an era, perhaps relatively recent on cosmic timescales, where the conditions for forming large gas-rich planets are especially favourable. That suggests that the largest planets might be more common in certain epochs of the universe's history than in others. There's also the role of technology in shaping our answers. Our current telescopes and missions are sensitive to certain kinds of planets in certain kinds of systems. They are particularly good at finding large planets close to their stars. As new instruments come online, especially ones designed to directly image planets, or to study faint signals from more distant systems, our view of what exists may change. The James Webb Space Telescope is already pushing into new territory by studying the atmospheres of exoplanets in unprecedented detail. Future missions are planned to directly image Earth-like planets, but along the way they may also reveal new classes of giant planets in wide orbits. Ground-based observatories with extremely large mirrors are also being built. These will have the resolution and sensitivity to study stars and planets in regions of the galaxy that are currently difficult to access. So part of the answer to whether larger planets exist is tied to whether we will be able to find them. There's a subtle distinction here between physical possibility and observational possibility. A planet might exist that is larger than anything we've seen, but if it doesn't transit its star, doesn't cause a strong stellar wobble, and isn't bright enough to be imaged directly, it might remain invisible to us for a very long time. So our current list of largest planets is a list of the largest planets we can see with our current methods. That leaves plenty of room for surprises. Another idea that sometimes enters these discussions is whether truly enormous planets could form in environments very different from typical star systems. For example, in the dense regions of star clusters, where stars pass relatively close to one another, disks can be disrupted, merged, or reshaped. In such environments, material from one disk could be captured by another star, potentially creating unusually massive disks. A planet forming in such a disk might have access to an unusually large supply of gas. These are speculative scenarios, but they highlight how varied the universe can be. the standard picture of a star forming in relative isolation with a neat, tidy disk, is not the only possibility. There are also galaxies with very different properties from the Milky Way. Some are rich in gas, some are undergoing bursts of star formation, some have low metallicity, others high. Each of these environments offers a different set of initial conditions for building stars and planets. So when we ask about the largest possible planet, we're really asking about the range of conditions the universe can produce. There's also a conceptual limit that comes from definitions. At some point, an object becomes so massive that calling it a planet becomes awkward, regardless of how it formed. If it can sustain nuclear fusion, even briefly, it starts to behave more like a star. So if we're strict about that boundary, then there is a ceiling on how massive a planet can be. But that ceiling doesn't necessarily limit how large it can appear by radius, because as we've seen, mass and size don't always scale together. So the largest looking planets are often not the most massive. They are the ones that have found a way to spread out, to stay hot, to hold onto a thick atmosphere. That suggests that if even larger planets exist, they might be in the same general category. Hot, low-density, gas-rich worlds in close orbits, or young, glowing giants still cooling from their formation. There's also the question of whether we might eventually find planets that are, say, 3 times the radius of Jupiter. Most models suggest that this would be very difficult to sustain. At that size, the atmosphere would be extremely loosely bound, and escape rates might be very high. But the universe has a habit of finding ways around our expectations. Maybe there are combinations of mass, composition, and heating that allow for more extreme inflation than we currently understand. Maybe there are atmospheric processes that can maintain extended envelopes more efficiently. Or maybe the planets we've already found are brushing up against the true limits, and what we'll discover next is not something bigger, but a clearer understanding of why things stop where they do. Either outcome would be valuable. From a human perspective, there's something calming about holding this question open. It reminds us that our knowledge is a work in progress, that the universe is not something we've finished exploring. Every new planet discovered, especially one that stretches the boundaries of what we thought was possible, adds another piece to a puzzle that may never be fully complete. As you sit with the idea of these possible worlds, you might imagine a distant star far beyond the reach of our current surveys. Around it, perhaps, a planet larger than any we've catalogued so far moves in a slow, steady orbit. Its atmosphere might be glowing with heat, or drifting outward into space. Its existence might be marked only by a tiny regular dimming of its star's light that no one has noticed yet. That thought doesn't demand an answer. It simply invites a sense of openness. From the moment we begin to compare our small familiar world with the vast, distant giants that circle other stars, a subtle shift takes place in how the universe feels. It stops being a backdrop and starts becoming a kind of story, one that unfolds through patterns, limits, and quiet hints about how everything fits together. The largest planets we've found so far are not just impressive because of their size. They are meaningful because of what they reveal about how the universe builds things, how it changes them over time, and how much room there still is for surprise. When astronomers study these giant worlds, they aren't only trying to understand the planets themselves, they're using them as tools, as markers that point toward deeper processes. A very large planet carries within it a record of the environment it formed in. Its mass, its composition, its orbit, and its size are all shaped by the disk of gas and dust that once surrounded its star, by the chemistry of that material, and by the gravitational interactions that followed. So in a sense, each giant planet is like a fossil. Not a fossil of a living creature, but of a formative era, a time when a young star system was still in motion, still deciding what it would become. One of the first things these giants tell us is that the universe does not favour a single blueprint. For a long time, our own solar system was the only example we had. Rocky planets close to the sun, gas giants farther out, everything in relatively calm circular orbits. It felt orderly, almost designed. Then came the hot Jupiters, the superpuffs, the massive worlds in tight, fast orbits that didn't fit the pattern at all. Their existence showed that the layout of our system is not a universal rule. It's one outcome among many. This realization changes how we think about planet formation. Instead of a single, predictable process, we now see a range of possibilities. Some systems build giants early and let them migrate inward. Others keep them far out. Some never build giants at all. Others build several. The giants, especially the largest ones, sit at the extremes of this range. They show us what happens when conditions push planetary growth toward its upper limits. Another thing these worlds reveal is how strongly stars and planets are linked. A planet's size and structure are not just the result of what it gathers during formation. They're also shaped by what its star does to it over time. When we look at an inflated giant planet, we're often seeing the long-term effect of radiation, stellar wind, and gravitational interaction. The star heats the planet. The planet responds by expanding. The star's gravity pulls on the planet. The planet responds by flexing and heating internally. This ongoing exchange turns the star and planet into a kind of coupled system, where changes in one can lead to changes in the other. That idea extends beyond individual systems. It suggests that the properties of planets across the galaxy are tied in a broad way to the properties of their stars. The mass of the star, its temperature, its age, and its chemical makeup all influence what kinds of planets form and how they evolve. By studying large planets around different types of stars, astronomers can begin to map out these relationships. They can ask questions like whether larger stars tend to host larger planets, or whether stars with more heavy elements are more likely to produce gas giants. The answers to these questions help build a picture of how common different kinds of worlds might be in the universe. There's also something to be learned from where these giants are found. The fact that many of the largest looking planets are close to their stars tells us that migration is a common process. Planets don't always stay where they're born. They move. This movement reshapes entire systems. A giant planet moving inward can clear out material, scatter smaller planets, or change the orbits of worlds that remain. So the presence of a large planet in a tight orbit hints at a more dramatic past, a time when the system was more crowded and more chaotic. That history matters when we think about the broader question of habitable environments. The path a giant planet takes through a system can influence whether smaller, rocky planets end up in stable, life-friendly orbits or are pushed into inhospitable regions. So in an indirect way, the study of these giant worlds connects to the search for life elsewhere. They are not just objects of interest in their own right. They're actors in the larger drama of planetary systems. Another message these planets send is about the behaviour of matter under extreme conditions. Inside a giant planet, pressures and temperatures reach levels far beyond what we can recreate in laboratories on Earth. Hydrogen becomes metallic. Electrons move freely. Materials take on properties that don't exist under everyday conditions. By modelling these interiors and comparing predictions with observations, scientists can test theories about how matter behaves when it's squeezed and heated to such extremes. This has implications that go beyond planetary science. It touches on physics more broadly, on how elements and compounds behave in environments that are rare in our corner of the universe but common elsewhere. So a large planet becomes a kind of natural experiment, one that the universe is running continuously and that we are trying to observe from a distance. There's also a lesson here about time. The giants we see today are not necessarily the giants that will exist tomorrow or that existed in the past. Planets change, they cool, they lose atmosphere, they migrate. Their stars change too, growing brighter or fainter, more active or more stable. So when we study a large planet, we're seeing a moment in a long story. That moment is shaped by billions of years of prior events, and will, in turn, shape what comes next. This perspective encourages a kind of patience in how we think about the universe. It reminds us that what we observe is always a snapshot, not a final state. Another thing these worlds tell us is how much our own understanding depends on our tools. The fact that we've found so many large, close-in planets is partly because those are the easiest to detect. So the universe we see through our data is not a perfect mirror of the universe that exists. It's filtered by our methods. The giants highlight this bias. They show up clearly in our surveys. Smaller, more distant planets are harder to find. So the current picture of planetary populations is weighted towards certain kinds of worlds. Recognizing this helps scientists design better instruments and missions. It shapes where they look and how they interpret what they find. There's also a broader, almost philosophical message in all of this. The existence of planets so much larger than our own challenges our sense of what is normal. On Earth, we tend to measure things in human terms. A large building, a wide river, a long journey. These scales make sense in our daily lives. But when you start thinking about a planet that could hold thousands of Earths inside it, those everyday measures lose their meaning. The giants force us to adopt a different frame of reference. They push us to think in terms of planetary scales, stellar scales, and galactic scales. That shift can be strangely calming. It places our own concerns in a wider context. It reminds us that we are part of a much larger system, one that has been unfolding for billions of years and will continue long after we're gone. Another insight these worlds offer is about diversity. Not just the diversity of planets, but the diversity of outcomes in general. The same basic ingredients, gas, dust, gravity, and time, can produce rocky worlds like Earth, ringed giants like Saturn, puffed up super-Jupiters, and faint brown dwarfs. The differences come from subtle variations in conditions and timing. This suggests that the universe is not fine-tuned to produce one particular kind of world. It is capable of producing many across a wide range of possibilities. That idea carries over into how we think about life and habitability. If the universe can build such a wide variety of planets, it may also be capable of supporting a wide variety of environments. The giants themselves may not be friendly to life as we know it, but their moons, their influence on systems, and their role in shaping planetary architectures can create conditions where smaller, more temperate worlds can exist. So in a roundabout way, the study of large planets contributes to the broader question of whether we are alone in the universe. There's also a practical side to this knowledge. Understanding how giant planets form and evolve can help scientists interpret observations of young star systems, disks, and stellar environments. For example, when astronomers observe a disk with a gap in it, they might infer that a large planet is forming or has already formed there, carving out that space. By understanding what kinds of planets can create such features, they can better understand what they're seeing, so the giants become part of a toolkit for studying not just planets, but the broader process of star and system formation. Another message these worlds carry is about limits. We often think of the universe as boundless, and in many ways it is. But the behaviour of large planets shows that there are constraints. Gravity, pressure, temperature, and nuclear physics all impose boundaries on what is possible. You can't make a planet arbitrarily massive without turning it into something else. You can't make a planet arbitrarily large without running into problems with atmospheric escape or structural stability. So the largest planets we find are not just curiosities. They are signposts that mark where one set of physical rules gives way to another. In that sense, they help map the edges of planetary space, the region of possibility where planets exist and beyond which stars begin. This idea of edges and boundaries is a recurring theme in science. We learn a lot by studying the extremes, the hottest stars, the coldest regions of space, the largest planets, the smallest particles. These extremes test our theories. They reveal where our understanding works and where it needs to be refined. So the giants serve a similar role. They sit at the edge of what we consider planetary, and by doing so, they help sharpen our understanding of what a planet is. There's also an emotional dimension to this, even in a calm, reflective way. Thinking about these worlds can inspire a sense of wonder that doesn't rely on drama or spectacle. It comes from the quiet realization that the universe is capable of building things on scales we can barely imagine, and that we, small as we are, have found ways to notice and study them. This connection between the very small and the very large is part of what makes astronomy feel special. A tiny change in a star's brightness, measured by a sensitive instrument on a distant planet, can reveal the presence of a world that dwarfs everything we know. So the giants tell us something about ourselves too. They tell us that curiosity and careful observation can bridge enormous distances. They tell us that understanding doesn't always require proximity. Sometimes it just requires patience. The picture that emerges is not just of a universe filled with big planets, but of a universe filled with patterns, processes, and possibilities. The largest planets are like punctuation marks in that larger story. They don't define the whole narrative, but they draw attention to important moments, important transitions, important questions. Here, after wandering through distant systems and enormous worlds that stretch the idea of planet to its edges, the focus begins to soften and slowly turn back towards something closer, something familiar. The journey outward has been about size, mass, heat, and gravity, about numbers that grow so large they almost lose their meaning. But the journey back carries a different kind of weight. It's about what those distant giants quietly do to the way we think about our own small place in the universe. When you look at Earth from the surface, everything feels large enough. The sky seems endless. The ocean feels boundless. Mountains look immovable. Distances stretch into hours, days, or weeks of travel. In the scale of everyday life, our world is already vast. Then you learn about a planet that could hold 1,000 Earths inside it, and that sense of scale gently shifts. It doesn't erase the importance of what's close, it reframes it. The idea of a giant planet, swollen and glowing near its star, drifting through space, as part of a system so far away that its light takes centuries or millennia to reach us, adds a quiet layer of perspective to the ordinary. It reminds us that the universe is not built around what feels large to us. It's built around rules and processes that operate across ranges of size and time that we can only partly imagine. And yet, all of our understanding of those distant worlds comes from this one. From a small rocky planet orbiting a medium-sized star in a fairly ordinary part of a fairly ordinary galaxy. That fact alone carries a kind of quiet symmetry. The smallest and the largest are connected by the same act of looking. One of the things these giant planets do, almost without trying, is challenge the idea that importance is tied to size. A world can be massive, wide, and powerful in terms of gravity, and still be, in a sense, empty. A gas giant has no solid surface to stand on, no place where a human story could unfold in the way it does here. Earth, by comparison, is small. But it's dense with detail. It's layered with oceans, forests, cities, and histories. Its surface is active, changing, shaped by weather, life, and time. So when you hold the idea of a super Jupiter and the idea of Earth in the same thought, something interesting happens. The contrast doesn't make Earth feel insignificant. It makes it feel specific. It highlights the fact that our world is not just one more object in a catalogue. It's the place where catalogues are made. There's also something grounding about the way planetary science circles back to this point again and again. We study distant worlds to understand how planets form, how they evolve, and how they interact with their stars. And in doing so, we learn more about how our own planet came to be. The giant planets in our solar system, for example, likely played a role in shaping Earth's history. Jupiter's gravity may have influenced the delivery of water and other materials to the inner planets. It may have deflected or redirected comets and asteroids, changing the impact environment in which life eventually emerged. So even here, on this small world, the presence of a giant has mattered. When you extend that idea to other systems, it becomes clear that every planet, large or small, exists as part of a network of influences. A supersized planet close to its star can reshape the entire system. It can clear out material, shift orbits, and determine which smaller worlds survive and where they end up. So the giants and the small worlds are not separate stories. They're chapters in the same, larger process. Another gentle realization that often comes with thinking about these extremes is how much of the universe operates outside the range of our direct experience. We live in a narrow band of temperatures, pressures, and timescales. Step too far outside that band and things become unfamiliar very quickly. The interiors of giant planets are places where hydrogen behaves like a metal. Their atmospheres host winds that move faster than anything on Earth. Their magnetic fields can stretch millions of kilometers into space. These are not environments we can ever visit or fully recreate. And yet, through observation and modelling, we build mental pictures of them. We use math, physics, and imagination guided by data to extend our understanding into places we will never physically go. That act itself is a kind of quiet achievement. It's a reminder that exploration is not limited to travel. It can happen through thought, through careful measurement, through a willingness to follow small clues to large conclusions. There's also a subtle comfort in the idea that, for all the variety and scale in the universe, the same basic rules apply everywhere. Gravity works the same way on Earth as it does around a super Jupiter. Light behaves the same way here as it does around a distant star. The difference is not in the rules, it's in how they play out when you change the conditions. That continuity creates a sense of connection. The planet we stand on and the largest planet we've discovered are part of the same physical story. They're shaped by the same forces, even if those forces express themselves very differently in each case. When you let that idea settle, it becomes easier to see our own world as part of a much wider pattern, rather than as something isolated or separate. There's also something quietly humbling about the way these discoveries are made. The largest planets in the universe are not found by building bigger and bigger machines and reaching out to touch them. They're found by noticing very small things, a dip in a light curve, a shift in a spectrum, a pattern in a stream of data. From those subtle signs, entire worlds are revealed. That contrast between the scale of what is discovered and the scale of the signal that reveals it speaks to a kind of balance in the way knowledge grows. Big ideas often rest on small observations, and those observations in turn depend on patience. Astronomy is not a science of quick answers, it's a science of long watching. Stars change slowly. Orbits repeat over days, months, or years. Data accumulates bit by bit. So when a new, oversized planet is confirmed, it's often the result of years of work by many people, each contributing a piece to the picture. That collaborative, gradual process is another way the study of giant worlds reflects something human. It shows how understanding is built collectively, over time, rather than all at once. There's also a kind of quiet continuity between the ancient and the modern in this field. For thousands of years, people have looked up at the sky and noticed the bright wandering points of light that we now know are planets. Jupiter was one of those points. Today, we look at stars that are too faint to see with the naked eye, and notice even fainter changes in their light. From that, we infer the presence of worlds far beyond anything ancient observers could have imagined. And yet, the basic act is the same. Looking up, noticing patterns, wondering what they mean. The scale of the universe hasn't changed. Our tools and our interpretations have. Thinking about the largest planets also brings up the idea of limits in a more personal sense. It reminds us that there are things we may never fully know.